I am Vahid Cheshmsiahi, PhD student from Russian State Hydrometeorological University, St. Petersburg, Russia. My presentation is on big waves under polar laws based on altimetry measurements and model simulations. Nowadays, the functioning of Northern Sea route in Arctic is increasing, so the development of hydrometeorological forecasting systems are required, in particular surface wave prediction. Of course, models like one, WaveWatch3, etc., are certainly capable of giving vast information about waves, but the computing power limitation and need to use high spatial resolution wind fields, leading the developers to produce and develop simpler and faster solutions. Kudryavtsev and co-authors in 2021 proposed a parametric model of generation and evolution of waves in wind fields that change in space and time. The main purpose of this work is to apply the model of Kudryavtsev and co-authors to study the big waves generation by polar laws in Arctic seas and compare the results with altimetry measurements. The complete system of equations are coming from the work of Kudryavtsev and co-authors, which are presenting wave train position, modified energy, spectral group velocity, and spectral peak direction. The parameters of these equations are given in different forms of relations. The system describes the development of surface waves under a varying wind field in both space and time, and the evolution of swell propagation in the absence of wind forcing. Kudryavtsev and co-authors in other work considered the proposed model to study generation of waves under tropical cyclones. So what is the difference of tropical cyclones and the polar lows? In general, tropical cyclones have symmetric radial distribution of wind speed, while polar lows are mostly symmetric and the wind field have coma shape mostly. Unlike tropical cyclones, the trajectory and radius of polar lows vary greatly in space and time, and their lifetime is short, from hours to days. Under the conditions of polar lows, the air temperature is negative and the certification of the atmosphere is highly unstable. So these conditions of polar lows lead us to apply few modifications on the proposed or original model. These modifications are including drag coefficient parameterization using Quare3 algorithm, and the introduction of the dependence of air-sea density ratio on air temperature. Both parameters, I mean drag coefficient and air-sea density ratio, affect on wave growth rate, which you can see at the end of this slide. So the grid that we used in this study has a 20 by 20 kilometers spatial resolution, atmospheric data coming from ERA5 reanalysis, sea ice concentration from the University of Bremen, and altimetry measurements of significant wave height that we used are coming from Altica, Sentinel-3, and Curiosat-2. Model simulation procedure is as it's shown in this sketch. The model reads ERA5 and ice concentration data and applies Iceland mask on data and generates the grid, and then the solution starts from the initial conditions using duration limitation laws and then the equations get solved by Runge-Kutta fourth order scheme. So at the end that we have a massive cloud of data, we need to split this data by mn wave families. I mean, for in given time, we need to have hourly maps of significant wave height, wavelength, and wave direction. For this purpose, at each spatial grid, we calculate total energy, average wavelength, and average wave direction. And as I said, at the end, we have hourly maps of wave parameters. The data that we gathered for both areas of study, including Barents and Norwegian Sea, are as shown in these two figures. Polar laws were chosen from Rocco 2019 work, and for both area, I mean for each area, we gathered almost 40 altimeter tracks for significant wave height measurements. Here we have the hourly evolution of wind, field, significant wave height, and wavelength from left to the right. So as we see, polar law is generated in the west side of Barents Sea. It moves to the center and then changes its direction to the south, while it moves from the west to the center. The strong wind area is located in the rear sector of the polar law, and waves generated under strong wind, but as immediate as it changed the direction to the south, waves enter to the resonance effect or get trapped under strong wind, because the location of the location of storm area gets to the right sector of the cyclone. So waves get trapped and they gather energy and momentum abnormal to the abnormal level up to the 12 meters and 350 meters for significant wave height and wavelength respectively. Sorry. Here we have the time evolution of cyclone parameters and wave parameters. In the right panel, we see significant wave height and wavelength shown by blue and red lines respectively. As we see, when polar law turns to the south, as shown by polar law's turning point, the increment of significant wave height and wavelength become two times as its first phase of motion, but they don't become higher than Pearson-Moskowitz level for fully developed waves. Here we have the comparison of wind and significant wave height for first polar law. The results, I mean, the comparison are shown when the altimeter track crosses the storm area of polar law. As we see, the modified model, which shown by red lines, gives better results than original models. So the modifications were necessary in this study. And also the results of modified model, some in most of points are one-to-one to the altimeter measurements. Here we have the second polar law, which were happening in Norwegian Sea between 14 to the 17 of January 2019. From the first hours of its generation, strong wind area is located in the right sector, so immediately waves get trapped in the right sector and they gather energy and momentum. And as we see, significant wave height becomes up to 12 meters and wavelength up to 300 meters. Again, here we have the comparison of model simulations with altimeter measurements for the second polar law when tracks cross the cyclone's storm area. As we see, again, the modified model has better results than original model. In some area, I mean, in the south part of Norwegian Sea, we have underestimation from model that can be because we didn't consider waves coming from Atlantic Ocean. Here is the scatter plot of model simulations and altimeter measurements. Again, these figures also prove the capability of the modified model in good simulation of significant wave height. So in conclusion, we can say that the suggested simple parametric model is a good instrument for wave prediction in Arctic seas. And as we saw, the group velocity resonance is responsible for abnormal big waves generated by moving polar laws. But this resonance effect or trapping effect it happens when the storm area is located in the right sector of the polar law. Thank you for your attention.